Hi, this is Kerry McNamara again at Bossier Parish Community College, and I want to take you through a little bit of what I call chemical recipe working, or as your textbook will probably call it, stoichiometry, which is a funny word to say, harder to spell, and a lot of students really get thrown by this. But all it really means is taking a chemical reaction like we showed before, a balanced chemical reaction, thinking of it as a recipe, and then predicting how much product we can make given a certain amount of ingredients. Okay, for example, let's say you have a recipe for something simple, like a 3-egg omelet, okay? And you've got 7 eggs, okay? Each omelet, each serving, takes 3 eggs, so with 7 eggs, you can only make, what, 2 full omelets and maybe a little tiny omelet, okay? But 2 full omelets. Or let's say your recipe is for 2 servings, cooking for 2, but you're only serving 1, maybe yourself. What are you going to do with that recipe? With all the ingredients, doesn't mean you can't make the recipe. You just need to cut everything in half to make half as much. We're going to show that with a chemical reaction here through what I call chemical recipe working through stoichiometry. Okay, so behind me here, I've gone ahead and put up a chemical reaction, and I'll walk you through it. We can tell right away because of the coefficient blanks out in front of everything that the reaction is unbalanced, so we'll walk through the balancing again. But basically what we have is a chemical recipe using for ingredients lithium oxide plus sodium nitride, creating lithium nitride and sodium oxide. Now you may have heard me say those same words, just kind of switched up a little bit, and that's the hallmark of what we call a double replacement reaction, which isn't really important here. Okay, but we're going to show how to work this recipe with a given amount of starting material. So, first thing we need to do in stoichiometry, step 1 is what we learned before, make sure the reaction is correctly balanced. So let's go through it again. Let's make a list of the elements that we see on both sides: lithium, oxygen, sodium, and nitrogen, and we'll do the same thing on the product side in the same order, remember, even though they're out of order on the other side. And then sodium and nitrogen. And let's take a head count of what we see on both sides. So here I have 2 atoms of lithium, 1 atom of oxygen, 3 atoms of sodium, and only 1 nitrogen. On the product side, we have 3 lithiums. Let's see, oxygen is way over here now, only 1 of them. Nitrogen back over here, 1 of them. I'm sorry, that should have been the sodium. Nitrogen is only 1, and the sodium we actually have 2 of them. Okay. So let's proceed. Remember, our order is to go metals first. So the metals, the elements on the left-hand side of your periodic table, those would include, let's see, the lithium is a metal for sure, and the sodium is a metal. And right now we've got the old 2 and 3 and 3 and 2 numbers. So again, let's think 6. Let's just take one element at a time though. Let's do the lithium first, since it's the first on our list. So a 2 for lithium on this side, 2 atoms of lithium, and 3 on this side. Again, the numbers aren't going to match up on the number line until we reach 6. So let's be bold here and not worry about who we may upset as far as the other elements. Let's get the lithiums balanced. Let's get 6, in other words, on both sides. So to make 6 lithiums on this side, I'll put a 3 here to make 6 lithiums. What else does that do? It made 6 of those, but it also makes 3 oxygens. Okay. And then to make 6 lithiums on this side, we have 3 here already, so we just need a 2. And that's going to make 6 lithiums for us. And it's also going to change our nitrogen up to 2. Okay. Let's take the other metal, the sodium. 3 sodiums on this side and 2 on that side. Well, really the same thing. Let's try that and see if that works for us. Let's put, to make it 6 on both sides, let's put a 2 in front of this to make 6 sodiums. What else does that affect? Makes 2 nitrogens. And let's put a 3 over here for the sodium to make 6 sodiums, and it also makes 3 oxygens. Now here's a neat thing about balancing. When you go one element at a time, oftentimes you find The other elements just kind of came out in the wash being balanced. Let's look at our numbers now. 6, 3, 6, 2. 6, 3, 6, 2. We appear to be completely balanced right out of the chute just by balancing the metals first. Now the coefficients aren't these numbers. The coefficients are actually 3, 2, 2, 3. Okay, but we're balanced. And that's, again, the first step in any stoichiometry problem. I often tell my students, if you can't get the darn reaction balanced with stoichiometry in the first step, go ahead and fake it. Put in some numbers and pretend it's balanced. Okay, it doesn't mean you can't continue with the next steps I'm about to show you. Okay, but here we have a nicely balanced chemical reaction. Okay, now let me tell you something I didn't mention before when balancing. What these blue numbers really mean. In a regular recipe in the kitchen, we have units like teaspoons or cups or ounces. In chemistry, we don't mix things up like that. That can get too confusing. What these numbers here in blue, 3, 2, 2, 3, stand for are what we call moles. Moles, like a little furry animal, the mole. A mole is a whole bunch of atoms, or molecules in this case. But it's our unit of chemical measurement that we'll use for chemical reactions. Now, what we usually get in a chemical reaction to start with for ingredients is a measurement not in moles, but rather in grams. Our scales in our laboratories and in our classrooms don't measure in moles when we put something on a scale. They measure in grams. So we're going to have to tackle that problem here in just a sec. But let's just imagine, I'll make something up here. Let's say we start with 50 grams of lithium oxide. Okay? Notice it's in grams. This calls for, the recipe rather, calls for 3 moles of lithium oxide. Well, maybe we have exactly 3 moles here. We don't know yet. Even if we don't cancel the whole recipe. Just like I said before, we can double recipes, cut recipes in half, triple recipes. Just what it says in the book doesn't mean that's what we're tied into. So let's see if we can't continue here with the recipe given our starting material. 50 grams of lithium oxide. That's in grams. These blue numbers, again, are in moles. So we need to change this to moles. And you've probably seen converting from grams to moles is very easy. But you need your periodic table, most likely. All we need to do, ignore this part for a second, is figure out from our atomic weights on the periodic table what each of these atoms weighs. So if you look up lithium, you'll see it says, I think, 6.941. I tell my students to just, let's round that to 7. And there's 2 lithiums here. So that's 7 plus 7, which gives me 14. And then oxygen, 15.9994. Let's call it 16. Okay? So we have 16 for the oxygen. Adding those 2 numbers together, 14 and 16, we get 30. And that means 1 mole of lithium oxide weighs 30 grams. Okay? And this conversion factor, which is really just equal to the value of 1, is going to help us convert from grams to moles. So we can speak the language of the chemical reaction, the language of the blue numbers, in other words. Now when we do the multiplication here, and really it's going to be division, it looks like, in this case, notice the units cancel. Grams on top cancels grams on the bottom, because think of this really just over an imaginary 1. Okay? And the unit that comes out is going to be moles. So we're in good shape already. And this is going to be moles of lithium oxide. So let's do the math. And if you take your calculator and just divide 50, well, first you can go 50 times 1 divided by 30. You should get, rounding off a little bit here, 1.67 moles of lithium oxide. That's what we found in the cupboard, in other words. That's what we found when we raided the pantry. We didn't have, apparently, 3 moles of it. We only have about 1 2/3, or 1.67 moles. Okay? The point is, we don't cancel the reaction. We continue on, but what we're doing, in effect, is scaling down the reaction. Not quite cutting it in half, but close to it. So, before we proceed, if we're not starting with 3 moles of lithium oxide, we shouldn't really expect to get 2 moles of lithium nitride or 3 moles of sodium oxide, because we're not starting with what the recipe calls for. But we continue on. So let's keep that 1.67 moles there. I'll get rid of our work. And what I'm going to do is take that answer, 1.67 moles, not cross out my 3. I want to keep my 3 there. But I'm just going to place that 1.67 underneath the coefficient from the balanced reaction. Now, we haven't even asked ourselves what we're trying to make here. Let's imagine we're trying to predict how much of lithium nitride we can make. Okay? We don't know how much we're going to be able to make. We don't have 3 moles, so we shouldn't expect to get 2 moles of lithium nitride. In fact, we're probably going to get less. But let's go ahead and just put as a placeholder, kind of like a question mark, an X there. What that sets up for us, guys, is 2 fractions. Okay? Not that L. And a fraction there. This sets up what's called the molar ratio step. Now that we've got that, we can get rid of this. And let's go ahead and just set these 2 fractions equal to each other. This is the step that scales up, or in this case, scales down our recipe based on how much we start with. So again, we didn't start with 3 moles of lithium oxide. We only have 1.67 moles. We put an equal sign here and set it equal to this fraction, 2 over x. And our goal here is to solve for x. Now, based on your familiarity with algebra, you may solve this for x many different ways. My preferred way, and what I kind of encourage my students to do, is do the cross multiplication. In other words, go that direction, catty corner wise, 3 times x, and we'll just write this over here, 3x. Set that equal to the other catty corner direction, 2 times 1.67, and 2 times 1.67 gives us approximately 3.34. Okay? And when we divide, again, we're trying to solve for x here. Now we have 3x, so we want to get the x all by itself. Just divide both sides by 3, and we should get something like this. X is equal to, approximately, rounding off a little bit, 1.11, and this will be moles of lithium nitride. So what we can do now is take this x out and put what we should expect to make, which is 1.11 moles. And let's step back and take a look at this. In our balanced reaction at the beginning, if we had started with 3 moles of lithium oxide, we would expect to make 2 moles of lithium nitride. Well, we didn't have that to begin with. Remember, we only had, I think it was 50 grams of lithium oxide, which came out to be 1.67 moles. So with less than 3 moles of starting material, we can't expect to make 2 moles of product. And in fact, we've just solved through a proportion what we should expect to get to make, 1.11 moles of lithium nitride. Now that, in a sense, is an answer. But again, if we're going to kind of judge ourselves on how well the recipe went, we want to be able to weigh it on a scale. So what we need to do is take this answer, 1.11 moles of lithium nitride, and convert that back to grams. So let's clean up the board a little. And let's take 1.11 moles, this is now for the product, of lithium nitride. And again, that 1-step conversion through multiplication, a fraction bar. 1 mole now on the bottom, 1 mole in this case of lithium nitride. And again, we need to use our periodic table to add up the atomic weights of all the atoms in our product. Now in this case, it's going to be 7, 7, 7, 3 lithiums, each at 7 for 21 total. And the nitrogen weighs still, in this case, 14 for a total of 35 grams per mole. Now canceling units, moles on top here again. Imagine that being over an imaginary 1. Moles cancel, mole on the bottom. And then 1.11, this time it's strictly multiplication. 1.11 times 35 gives us approximately, rounding off a little bit, what do we get here? About 38.9 grams of lithium nitride. Okay? And that's stoichiometry. That's predicting how much product we could make from a given amount of starting material. Now notice these 2 terms, the sodium nitride and the sodium oxide, really weren't involved in this recipe. They were there, but they were there in adequate amounts. Okay? In other words, we had plenty of this. we were limited in our amount of this. This is what's called the limiting reagent. More on that later. Okay, so if everything goes as planned, based on our original, think back, we had 50 grams of lithium oxide, we should expect to make 38.9 grams of lithium nitride. Well, not everything in a recipe goes perfectly. We spill things, things get dripped on the oven floor, let's say, or things are stuck in the mixing bowl. And let's just make something up here. Let's say someone actually did this reaction with that original 50 grams of lithium oxide, expecting to make, like we've shown on the board here, 38.9 grams of lithium nitride. We would call that the theoretical, because none of us got up out of our seats and went to the lab to actually do this yet, the theoretical yield. Yield just meaning how much we should produce, like a crop yield. Okay, so let's imagine someone goes to the lab with 50 grams of lithium oxide, expecting to make, like we predicted, 38.9 grams of lithium nitride. And when they come back and we measure it on our scale for them, we find that they only made, let's say, 27.3 grams of lithium nitride. Okay. Well, that's less than we expected them to make, but again, that happens most of the time in chemistry. We don't always make exactly what we expect to make because of the reasons we mentioned. Things get spilled. It's not so much mismeasuring things, but things get stuck to the beaker or to the test tube, or sometimes when a gas is produced, we don't capture all the gas and it kind of floats away. But that's our actual or real life yield. Okay, and again, I'm just making this up for our example. We'll call that the actual yield, what someone, some imaginary student or chemist, actually made in the lab when they actually expected to make the theoretical yield. What we can do now is grade them based on how well they did, or determine how well they did. This is called the percent, and there's nothing really chemistry involved here with this. This is the percent yield calculation. And all we do, this is very much like grading any exam or test. We take the actual yield, 27.3 grams, divided by the total that we expected to make, 38.9 grams, and then we just divide, well, what we should do to put it into percent is multiply by 100. You can see, because the numerator is smaller than the denominator, we're going to get something less than 1. But by multiplying by 100%, we'll put it into a percentage. And I think if you do this on the calculator, you should get somewhere, if you round off, somewhere near 71 to 72%. Let's just round up to 72%. Okay? Now, that's a C, I suppose, in most courses. But in chemistry, a 72% is actually a pretty good percent yield. Okay? I've never, in my experience, really gotten close to 72% yields. Chemistry isn't always that easy. Okay? 72% is a pretty good yield. Okay, so that's the steps for stoichiometry. And you can, with these types of problems, you can actually just make up your own stoichiometry examples. Just take any reaction, balanced or unbalanced, come up with a given amount of starting material, go through the steps we've shown here, grams to moles, and then we use the fractions, still in green here, set them equal to each other and solve for the missing piece. In this case it was, remember, x, and we got 1.11. And then taking those number of moles, just changing back into grams.